Hello everybody, welcome to our process control project where we implemented a 2D set point tracker. I'm Michael.
I'm Brett.
And I'm Mitch.
And let's get started. So to introduce you to the problem a little bit, the purpose of our project was to code up an automated shotgun turret that is able to track and hit clay pigeons when they're fired at any angle and initial velocity. So we implemented two different PI controllers that were used to track the X and Y coordinates of the pigeon.
So our variables in our simulation were the distance from the target in the starting position, which were our controlled variables. Our manipulated variables were the angle of elevation and the angle of rotation of our shotgun mount. Our set point was the pigeon location, and our process variable was the actual theoretical hit point of the shotgun. And we didn't include any disturbances in this model, but they could be, which we'll talk about later.
The equations were relatively simple. For the shotgun mount, they were just some ordinary differential equations that we could solve involving the angular velocity, both in the theta and the phi direction. For the pigeon flight, we just used some kinematic equations from physics, including a shift in the x and the y direction, depending on where we wanted the starting position of the pigeon to be. We had an initial velocity for our launch velocity and a launch angle, which we actually were able to randomize in our controller. The more difficult part of the math for our project was converting between the theta and phi that the shotgun was pointed into Cartesian coordinates for the plane where the clay pigeon was being fired. We had a couple of assumptions governing this, that there were no wind effects on the pigeon flight. Like Brett said, there were no disturbances that we had. Because we didn't actually have anything hooked up to a motor, we assumed that we were directly controlling just the angular velocity instead of inputting a power or a work into a motor. We also assumed there was no time delay between the controller and the process variable change. We also set some limits on our controller to make it a little bit more realistic, so that we had a maximum angular velocity so that it wouldn't be able to turn infinitely fast, or that it wouldn't turn in a complete circle or point straight up or straight down. Again, one of the more difficult things was converting between the coordinate systems, because the shotgun is operating in polar coordinates and the pigeon is flying on a Cartesian plane. But using some trigonometry, we were able to figure that out. These are some examples, these graphs, of some of the issues that we had with the math early on. We had kind of overcomplicated things with spherical coordinates and mixing up the x and y that the shotgun would be outputting. But in the end, we were able to get these issues resolved.
And so when determining which parameters of the PID equation were necessary, we ran three tests, one with a P-only controller, one with a PI controller, and one with a full PID controller. The P-only controller had a smooth arc, but left a lot of offset between our process variable and our set point. The PID controller tracked it pretty well, but had a lot of oscillations, which we don't want in order to calculate, when our process variable gets close enough to the set point to technically shoot it. So we went with the PI controller, which includes the integral term to close that that's offset, but it doesn't oscillate.
And so to talk about tuning parameters a little bit, initially we had to answer the question of whether or not we should use two different sets of tuning parameters for both the theta and phi controllers. We decided that since an equally aggressive response is required for both directions, that one set of tuning parameters would be adequate. So the tuning parameters that we decided on that gave the best response, if you look at these different pictures, was a Kc value of 10. It needed to be large enough to get a rapid target acquisition, but not too aggressive, and so that ended up being a really good value for that. We also included an integral term of about 0.005 in order to ensure there's no offset between process variable and set point. And then, like we said before, we did not include a derivative term due to resulting oscillations because of that. And so here's the application when we actually implemented our code based on our tuning parameters. You can see over here on the left that our code is actually hitting each different clay pigeon as it's being launched from, like we said before, random positions and random velocities. And those over here on the right are the side view and the top view of our controller as well.
Some opportunities for further research. We could add a third dimension. Like we mentioned before, we had the clay pigeon firing just in a single plane that was a set distance away from the shotgun, but we could have it firing diagonally to where that distance from the shotgun is constantly changing. We could also figure out ways to increase the number of pigeons that can be thrown. Our code kind of broke down when we added too many pigeons into it. It wouldn't graph all of them for whatever reason. We're not entirely sure why, so it could be that we need a more robust coding program or something like that. And obviously the biggest opportunity for further research would be the physical and actual implementation of this controller into a shotgun.
All right, so let's take a quick look at the code. If we pull it up right here. Essentially, all that you never ever really need to change is this value right here, the number of pigeons. We have it currently set at 3, but changing it to 6 will then launch 6 pigeons and allow our tracker to attempt to hit all of them. So if we come up here to run, save it, and we can see that there are 6 lines. Our tracker gets within a set distance, and that counts it as hit, and then it bounces to the next one. And then once it's completed, it returns to its original position. And then if you look at the output box, it comes up with this nice little thing that says it hit 6 pigeons, and then it gives you the time that the last pigeon was hit. So yeah, there's our code.